always.
circular in the middle?
Not always. No.
You're very close. You just got most of them.
It's
In
wrong
no.
everywhere.
in
Like
order
a
to get that
cyclone
one right,
wouldn't be, because if
you
you're going around like
kind of
this,
get all the others right. So
Yeah.
let it correct it.
right? And you do a curve going from this point to that point, you actually get the negative if you go from this point to that point, right? Because one is working against the field, one is working with the field. So if you do a work against the field, you get the negation of when you do a work with the field. So a field like that would be considered. But pictorially is not how we do it usually. We usually just do that check. dp dy is equal to dt.
Fudge!
Yeah?
Oh, my question was, number 17, it says to find that the path is independent.
I know, you're right.
You don't make that as
Thank you. You're right.
It has to be equal to 0, right? F, the line integral f dot dr has to be equal to 0.
No.
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 Just say gradient.
F dot dr around a closed curve would be 0
Okay.
if you know it's independent. It's not always 0.
Okay, because that's what.
It matters on the curve. To check if it's path independent, you have to check that a conservative function exists, which you would use the equation dp dy equals dp dx.
Okay.
Yeah.
I made a very stupid arithmetic mistake.
Don't worry about it. Any other questions?
Don't worry about it.
Can you find the potential function for something that is not conservative?
No, it won't work. That's what conservative means, right? A potential function exists.
Yeah.
It means you can write it as the gradient of some scalar function, right? So if it's not conservative, you won't be able to do that. Any other questions about the homework? Everyone got through the problems okay?
So,
Yeah.
like,
They were mostly
Then
computation.
well, if the
so
vector
the,
conservative, then f
like
is
a
gradient.
non-conservative field is
Yeah,
like
it'd be gradient.
the gradient, but times like a directional kind of
No, non-conservative just means it's not a gradient field. That's what it is.
Yeah.
So it could be
We
something
don't know
else.
if
related
it's
to
x,
a
y, and z.
function and into a
We don't know if it's x, y, and z,
how-
so we just leave it as gradient of that.
direction is like you
Mine doesn't have
actually-
pencil.
you find the partials, you I think you do cross products with no, it's not.
At least I'm not sure what you're talking about.
Yeah, okay.
Anyway, so we have vector fields and we can group them into two groups. Those that are gradient fields and those that are not. If you're a gradient field, you're what we call conservative, which means you're independent of path. In particular, it means if you do a line integral on a closed curve, you get 0. Yes?
So on a test, if you have evaluate the integral, whatever, and it's conservative, we could just skip all the work. But if it's not conservative, you're supposed to.
Yeah, you'd have to go through
Prove
it.
it.
Yeah. So on the quiz, for example, the last integral, you didn't have to do it. You just used the potential function, which I asked you to find in part 5. Yeah. So you weren't actually supposed to do the integral. If you do it, you would have wasted a lot of time.
I actually got one of the negatives wrong. Is that okay?
Well, it's not okay, I mean, you're not going to get a point.
It's a quiz.
I mean,
Yes,
if you're asking for an extra
Negative.
point, that's not going to work. Okay, well, if that's all the questions, I guess we're going to move on then. So remember, the first test is next Monday.
Yeah.
The review sheet has been up for a while. Make sure you actually go through all the problems in the review sheet.
Are you gonna be in the Zoom on Friday?
Yeah. So, by the way, in the review sheet, you would notice that there are Calc 3 problems there. They're actually about finding surface area, about finding arc length and all that. And this is not just me being cute. These problems are actually taken from finals. These do explicitly come up on finals. They're going to ask you directly about Calc 3 stuff. How to find a tangent plane, how to find a tangent line, how to find the surface area. All that stuff that you're actually asking. Right? So, and my test is going to try to be modeled off the final exam so that you're prepared for the final at the end of the day. So be sure you go through the review sheet.
You don't drop any tests, right?
I dropped one test.
Oh.
So we're getting 4, I dropped 1.
4.
Right. So the first 2 tests are going to be full length. It's going to be like the whole class. The last 2 tests are shorter, like 45 minutes.
The questions are sorted too?
Hopefully.
Yeah, the question will be shorter.
Of course.
But I really pack a lot in the first 2 tests. They have a lot of fundamentals in them. And
How many questions will be in the class?
it's like 5 or 6.
Wait, so it's like a, how long is that, an hour and a half?
The longer test would be like 5 or 6. It's roughly 15 minutes per hour. per question.
So it's like, wait, so it's a full hour and a half test?
Hour and 15 minutes.
So we don't get, okay.
Yeah.
You're gonna ask for definitions?
No, they're going to look like the finals. They're just going to be problems like in the review sheet.
And you'll trick us with one of them.
Yeah, I'll try.
Probably.
Okay, so now we're going to talk about Green's theorem. It's actually one of the three main theorems. So if you do a course in vector calculus, everyone expects you to know this theorem, right? It's sort of like if you do Calc 3, everyone expects you to know how to do a double integral. This is a very fundamental theorem in vector calculus. It, along with Stokes theorems and Divergence theorem, are the three main theorems that we're going to learn here. And basically what we're doing here is we learned about line integrals over vector and scalar fields, and we learned about last time the fundamental theorem for line integrals, where we actually said, well, if our vector field is a gradient function, then you can actually compute the line integral in the following way, right? If you have the gradient of f dot dr, then you can actually compute this line integral by doing this guy. And last time we also showed how to actually find that guy if you know that this is true. So that's one way you can do a line integral by doing something else, right? You don't actually do the line integral. Green's theorem is actually sort of the same thing. We're going to find another way to do a line integral when you know you're around a closed curve, right? And that's all Green's theorem is. It's going to connect a line integral around a closed curve to a scalar integral that you would be able to compute by knowing Calc 3. It's actually a double integral. Okay? And so just before we start, let me mention some things. Remember what we mean by orientation?
Yeah.
Yeah, yeah.
Right, direction in which you travel around the curve, right?
So it's important now. So I assume it's important now.
Huh?
So I
It's
assume-
going to be very important,
Okay.
right? So Green's theorem is dependent on orientation, right? And for closed curves, if you say positive orientation, what is that?
It's counterclockwise. Counterclockwise.
Counterclockwise, right? This means counterclockwise. Right? That we define to be the positive orientation, right? Of course, the negative orientation is the opposite.
But yeah.
Clockwise, right? So the orientation is going to matter here, so you should be aware of those definitions. Orientation just talk about direction. When we're talking about a closed curve, counterclockwise is the positive orientation. It's just a convention. That's how we do it. And clockwise is called the negative orientation. Right?
In this case, we'll only negate it, or we'll get like a totally different answer.
It will be negated, right?
Okay.
So, for example, you should also recall that if you're doing a line integral of a scalar function dx or dy, then that's equal to the negative of the negation, right? Right? So if you're doing a line integral around a scalar field with respect to x or y, then if you reverse the orientation, you actually negate the integral. That's also going to be a concept that you should be aware of, right? It's going to sneak in there in Green's theorem, right? Remember, if you do a scalar ds, then it makes no difference, right? Because ds is with respect to arc length. Arc length, it can't be negative, doesn't have direction. But x and y, they can be negative and positive, they have direction. So that's something you should keep in mind. Right, so basically, Green's theorem deals with closed curves, and I'd like to draw a picture, right? So if you know you're going around in this direction, and the problem will describe what direction you're going around in, we say this is positive orientation. Right? You're going around in this direction, we say that's negative orientation. Right? So keep that in mind. For Green's theorem, orientation matters. So all this is always in the back of your mind, okay? And now what we're going to do, we're just going to state Green's theorem and then we're going to use it right away, right? I'm not going to prove it. Even your book doesn't prove it in its full generality. It's really a long and messy thing. So let's first talk about the conditions and how it's applied. So notice that it's a positively oriented curve. That's a part of the theorem, right? The equation I'm going to say refers to positively oriented piecewise smooth curves.
So it's in the first quadrant.
Piecewise smooth closed curve. It doesn't matter what quadrant it's in. And here's finally the equation that you would have written down on the bonus problem. The integral along C of p dx, of course these are functions of x and y, I'm just leaving that up, plus q dy is equal to the double integral over d of the partial of q with respect to x minus the partial of p with respect to y.
Okay.
Right? This is an equation, right?
Okay. Move on. The A matters? Or is
Huh?
the A something is the A something conceptual with it, or?
No, dA just means the differential of the double integral. It means it would be dx dy or dy dx.
Okay. So
or
the area. Okay.
r dr d
Yeah.
theta.
Okay.
In other words, the line integral on the left. Right? In other words, if you want to compute this line integral, you know your C is a closed curve, you can actually do that double integral instead. And the obviously the benefit to this is that sometimes that might be a lot easier, right? Especially here we know that C could be a piecewise smooth curve. What if C has a lot of pieces, right? Like 10 pieces. It's going to be probably much easier to set up a double integral over that as opposed to parameterize 10 curves and do a single integral for each
You
of
never
those
do that.
curves, right? So yeah, so Green's theorem gives us another way
Right.
to compute this particular kind of line integral, which is just two integrals of the form f dx, right? So these guys, you notice that orientation will matter with these guys because they're the dx and the dy line integrals. Another thing you should notice is that Green's theorem is actually relating a line integral around a boundary curve to the region that it's bounding, right? And this is going to be a common theme. Stokes' theorem and divergence theorem does the same thing, but in higher dimensions. In Green's theorem, we're in 2 dimensions, and we're talking about a region and a curve that is the boundary of that region, right? So you can only apply it if you have a boundary curve. It's a closed curve and it's bounding some region. Then the line integral around the boundary is equal to the double integral over the region, right? That's what we're saying. Yes?
And the integral of p dx plus 2 dy is just equal to the integral of the vector function times dr? It's like the same?
It could be in a certain parameterization. It's more like, I did introduce this kind of line integral before. These are more, the line integral is more like this one, the f of x, y, dx. It's sort of the same thing, except you sort of put them together. This is the kind of line integral we have, right? Now with a certain parameterization, we could get f dot dr to look like this in 2 dimensions, if you parameterize the variables by themselves. But usually it's going to be, they're going to state the line integral, it's going to look like that form. Every now and again they ask you about f dot dr, but usually it's going to look like that. Okay? And that's it, that's all Green's theorem says.
Okay.
Right? So once you have all this stuff there, you know, C is positively oriented, it's a piecewise smooth closed curve, it's very important, right? D is the region bounded by the curve, then this equation will hold. Okay? Now, a note on notation. You might look in some other textbooks and you might see this notation, an integral with a circle around it, right? It's not a new form of integration. It just means, this literally just means we're integrating around a closed curve.
Is the same thing as a Gaussian surface?
No, it's nothing that complicated. It just means we're going around a closed curve.
That's
They might do that.
We nothing complex in this class.
And then there are some other mathematicians who are even more pedantic. They'll actually put an arrow on the integral to mean we're integrating around a positively oriented closed curve. So the integration is the same, they just might use this notation every now and then. Not everyone uses it, but if you see it somewhere, don't be afraid. It just means it's a line integral around a closed curve. Okay. Now let us do an example. A bunch of examples. Yeah, so that's all the theory you need to know for Green's theorem, right? You just need to know about orientation, what it means to negate it, and you need to know this equation. These conditions will usually be fulfilled, right? We'll always give you a piecewise positively oriented smooth curve. Well, we might not give you positively oriented, but you have to know how to change that. And we're going to do a problem where we actually change that.
So this is where we actually start using other coordinate systems like spherical and polar?
Spherical is only for
I know,
triple
I know.
integrals.
So
Yeah.
it's polar basically.
But polar could be applied here if your C is like a circle,
Yeah.
or part of a circle. Okay. All right, let's do some examples to see this guy in action. Example 1. Oh, this example I actually stole from your textbook. Problem 2 in the text. In the edition that I'm using. It says evaluate. problem might look like that. And by the way, usually on the final they do ask both, right? They'll ask you to actually do the line integral directly and then use Green's theorem to do it as a double integral. Right? So you should know both ways.
Will there be separate problems, or
No, that would be in one problem.
Okay.
Parts A and B.
So if they're the same, then you know you're right.
Yeah. Yeah. So that's the good thing about these problems, because you should get the same answer in both of them, right? Because Green's theorem says they should be the same. Okay. So everyone got that problem down? Okay, let's go. All right, so C is a positively oriented unit circle, right? So this is C, just the circle of radius 1. You're moving counterclockwise, right? That's C, which automatically means that this region here is going to be the D in the theorem, right? So C is a positively oriented unit circle, and D is the region bounded by that thing, right? So if you want to know where you're going to be doing the double integral over, the region that's inside the curve, right? That's what the theorem says. Okay, so let's do part A, right? Directly. How do we compute this directly? What do we need to do?
Polar. Parameterize it as using polar coordinates.
Yep.
So like x is equal to.
Right, parameterize, okay.
Parameterize.
Okay, so how would you parameterize it?
Cosine t.
Yeah. No.
X equals cosine t, right? Y equals sine t dx.
Negative sine t.
And so the line integral over C is equal to what? What are the limits? Zero to 2 pi, right? It's the full circle. Right? So let x be this, y be this. Those are your limits. That's dx, that's dy. Now you just go back to that guy and you plug in all the pieces, right? So it's 0 to 2 pi times the y is here, which is sine t, times dx, which is minus sine t, which that's just sine squared, minus the x, which is cosine t. Oh, let me write it out. Let me write it out so you guys can see. So this is sine t times minus sine t minus cosine t times cosine t. You can factor out dt and put it at the end. So this is the integral from 0 to 2 pi of minus sine squared plus cosine squared. How do you integrate that?
Wait, it's sine squared times. Never mind.
Right, it's 1, right? Don't be like using double angle formula or anything. That's just 1. Which gives you minus 2 pi. That's the answer.
Why is it? Never mind.
Huh?
Never mind.
So here comes the tricky part. Well, not tricky, but first time we're doing it. All right, so in Green's theorem, it says what? It says the integral of p dx plus q dy is equal to the double integral of partial of p with respect to x minus partial of p with respect to y. Right? Here, what is our p? What is our q? Minus x, right? So if I take py, that gives me what? 1. Qx would be minus 1. This implies qx minus py would just be minus 1, minus 2, right? Therefore, the line integral over C is going to be equal to the double integral over D of minus 2 dA. Right? Which, this is minus 2 times the double integral over D of dA, which we know is just the area of this circle. Right? So it also gives you 2 pi. This is from Calc 3. We know that the double integral of 1 dA is actually the area of the region, right?
Well,
Right. It comes in handy. You should know things.
okay.
Right. If you take the double integral over d of 1 dA, it actually gives you the area of D. That was something we learned in Calc 3. The triple integral over E of 1 dV is equal to volume. Right? So instead of actually setting up this integral, I didn't have to do it. I know D is just the area of this circle, which is pi r squared. R is 1, so the area is pi. And so I just have minus 2 times pi. The long way you could set up, I'd probably use polar, right?
Yeah.
You'd say theta goes from 0 to 2 pi, r goes from 0 to 1 of minus 2 r dr d theta, right? And if you did all that, you would end up here eventually. Right? Any questions?
Is that all?
That's it. That's Green's thing. That's using it. Right? And you're guaranteed to get a problem like this on the final. It always shows up in part 2 usually.
Will this be on our first test?
Huh?
Will this be on our first test too or no?
No, this is 13.4.
Oh, yeah.
First is up to 13.3. But that's it. Knowing Green's theorem is knowing this equation and being able to use one or the other. Right? And that's it. So the first one, doing the line integral directly, we've already learned to do that. The new thing really comes in by setting up this double integral, where you have to identify the P and the Q, find the partial according to the formula, and yeah, that's basically it. Of course, they might try to trick you with certain things, but that's basically the idea behind Green's theorem. Let's do another example. That's the problem.
So this is piecewise.
It's a piecewise smooth curve, which means if we were doing it directly, you need to set up 2 equations
Yeah.
and then plug it into that. Right? So, what does this picture look like? So we're going from the origin 0, 0 to 1, 1 along a straight line segment. Then we're going from 1, 1 back to 0, 0 along the cube. So that's going to be our guide. D is, of course, the region enclosed by this guy. And what do you notice about this curve? In terms of the things we should be looking for when we're applying Green's theorem.
It's closed.
It's closed, that's
That's
good,
not
so
green.
Green's theorem applies, so what else?
Negatively oriented.
It's negatively oriented, right?
Yes.
This is very important. It's negatively oriented. Okay.
Okay.
Which they never mentioned in the problem. But by doing this, you should know, oh, this is negatively oriented. You watch out for things like that.
Yeah.
Because as you just see, applying Green's theorem is sort of easy. These are the only tricks they can come up with to try to mess you up. Right. Like give you something that's negatively oriented without explicitly saying it. Right? These are things you have to look out for. Right? So it's a closed curve, okay, Green's theorem applies, but oh, it's clockwise. Right? So let's see how we do with this. Right? First of all, if we were to do this directly, what we would do is, right, we make the C1 and C2, right? C1, how do you parameterize it?
The line segment. From
So
0,
line
0
segment.
to
So your
0.
x would be what?
T. T.
Your x would be t, your y would be,
T.
and t goes from what? C2, how do you parameterize that? X is t, your y would be t cubed. T goes from
1 to 0.
1 to 0, right? So it's not, you can't write that as that. Your t would start at 1 and then go to 0, right? So you'd put 1 at the lower limit and 0 at the upper limit, right? So you'd have to, yeah.
What's NB?
Note.
No.
Just means
Not the
note.
line.
Yeah, note. It's French for note. Okay. All right. Now, if you were to do this, you're going to plug it in here. You're going to get huge, long polynomials. It's sort of annoying to do. Green's theorem would probably shorter, more than likely. We'll see. But we're asked to do Green's theorem way. So how are we going to do this? As always, you find the p and the q. Then you're going to find the py and the qx. What's p here? Py squared. Q as well. Qx.
PY squared.
Okay. So if you take qx minus py, you would get 3x squared plus 3y squared minus 3y squared, which is just 3x squared. Therefore, the line integral along C is just going to be the double integral over d of 3x squared dA. Right? How would you set up that integral? D is this region.
The upper bound minus the lower bound.
What's the limits on the outer integral?
How many is the
0 to 1.
0 to 1, so just flip it 1, 0.
0 to 1.
0 to 1. What's the inner limit?
1 to 0.
1 to 0. Oh wait, oh you're right. Okay, you're right. Yeah.
Yeah?
Yeah.
What's the inside?
Yeah.
Line
X. Well, like.
Oh, the x cubed.
Oh, you're right. You're right. Yeah.
It's going to be
X cubed is 0.
Yeah.
X cubed is X.
Yeah.
It's going to be 2 cubed to 0.
X equals 0.
Yeah.
You're right, actually, you're right. It is x cubed to x.
It's x cubed to x.
Look at the lines.
Okay? Count 3 people.
Oh, I get it. Okay.
Okay, remember how to set up double integrals, right? If you're looking at a double integral, this outside function, right, talks about constants, right? Right? And this guy talks about functions, right? And you go from the integral's bottom function up to top function.
That's y equals x.
Where bottom and top is, relative, right? This would be like dx or something. Like dy dx, right? If you switch to dx dy, top becomes right, bottom becomes left, right? But these are the constant limits from the x-axis, right? So this is the lower to upper usually, right? So we look at this guy and we said we want dx on the outside, which means dx should go between constants. That means the x goes, you look on the x-axis for the constant, right? It goes between 0 and 1. The y goes from this function up to that function. This is the bottom function, that's the top function. X cubed x, right? This is y equals x cubed, this is y equals x. Okay. All right, so that's the integral we have to do.
Well, no, we can't, because it's negatively oriented into this. The
Right,
orientation is
I
wrong.
was
So we
seeing
need
if
to
I
flip it.
caught you guys. Yeah,
So do we need this?
negatively oriented. All you have to do, boom,
Negative.
put a negative in front of it, and you're done.
Oh, that's easy.
I was seeing if I could get you guys to forget. Okay. Right? So the only thing different between positive and negative orientation is you just negate the integral overall, right? So because Green's theorem works with positively oriented, if we're using a negatively oriented thing, you just put a negative sign in front of everything, and that fixes it. So what do we get here? Integrate this with respect to y, with x for y. You plug in x, you get 3x cubed minus y minus this. This would be 1/4. So remember your Calc 3, remember how to set up double integrals, that's going to come back. In divergence theorem, you're going to have to set up triple integrals, so that's going to come back. So you need to remember these things.
After 13.5, I mean, is it 13.5 divergence theorem?
No, 13.5 is curl and divergence.
Okay.
All right, those are different operations we're going to do with vector fields. And for three-dimensional vector fields, the way you can test if it's conservative is to actually use the curl. So we'll talk about that next time. But today I just wanted to do Green's theorem. Let's do another example. So in one file, they actually drew a path. They never described it in words. So I decided to do an example like that. minus 3.
The four
This is
curve?
minus 1, this is minus 3.
Yeah.
Wow.
And it's C is this path, yeah.
That's all I didn't know.
Yeah. Or one double integral. Right? If you're doing this directly, of course, it's this monstrosity of a function, right? You're going to plug in parameterizations into that sine and cosine and all that stuff to get the circles, and then parameterize lines and plug into all that stuff. Crazy. On top of that, you're going to have to do C1, C2, C3, C4. Don't think so. We are going to use Green's theorem. We can get that out of the way in a single double integral. One double integral.
Professor, along the line itself, wouldn't the integral just equal 0?
Why would you say
From
that?
1 to 3.
How would you know that?
I don't know, previous example.
No, not necessarily. That's not a given. I mean, along this line, along the straight lines, your y is 0, which means that your dy would be 0 and your y here would be 0, but you still have this tan inverse thing to worry about, so it depends. It's not always the same. But yeah, that's our C. Of course, this would imply that D is just the region inside here, inside the half angle.
So you'll draw it in the actual test?
Yeah, they gave you this, right? They didn't tell you what D is, but they gave you
They
this.
drew this, okay.
Which, by the way, trust your computations. The drawing won't be to scale. In the final, when they gave you the picture, and you looked at it, it was like, that's definitely Pyro 4 right there. It wasn't, okay? So trust your computations. But here, it's clear that they're using semicircles here. Right? It goes from 3 to 3, 1 to minus 1, and they're on circular arcs. Right? So we're going to use Green's theorem, which means that I know the line curve for p dx plus q dy is equal to the double integral of qx minus p over d, where this is the d. Here, what's p?
Eq line within the square.
Negative
dy.
tan
Arctangent.
It's this one, right?
Yeah, follow the dx.
Because it's with the dx, right? Don't let them switch positions on you and trick you, right? They do things like this because really there's nothing else for them to do. All right, they're gonna try to trick you. Oh, well, let's make it negatively oriented but not say it, or oh, let's switch the dx and dy and not say anything, right? You have to be careful. Know the formula exactly. The p goes with the dx, right? So in this case, the p is actually the second term, right? Because that's the one attached to the dx, right? So your p is actually tan inverse x plus y squared. Your q is actually e to the y minus x squared. If you do p y, that's just 2y. You qx, that's just minus 2x, right? So we get rid of the arctangent and the exponential, right? So we're already looking easy. This implies that qx minus py would be minus 2x minus 2y, right? This means that the integral on C, we check counterclockwise, so it's positively oriented. We don't have to change the sign. So this is just a double integral over d of minus 2x minus 2y dA. Okay, how are we going to set up this integral?
0 to pi.
You want to use polar?
Use polar, yeah, that's how I do it. And how do you set it up? What are the limits?
Well, x is equal to r cosine theta. Well, yeah.
R is from 1 to
R is
3.
going from 1 to 3.
0 to 1.
R goes from 1 to 3. Well, I asked for theta first. I like to
Sure.
Zero to pi.
Yeah, 0 to pi.
0 to pi, R is going from 1 to 3. And your x you replace with r cosine theta,
Yeah.
y you replace with r sine theta. And what happens to dA?
R theta.
R dr d theta. Right? Actually, I've done 2 quizzes so far. You should know it by now. Right? So this is actually, you take the minus 2 out. This is r squared. Factor all the r's, bring it to the front.
It's going to become positive. Cosine theta plus sine theta.
Yes. So you do the r first, right, which you just r cubed over 3.
You could do Kumini.
This would be 9 minus a third.
Professor, couldn't you do Kumini?
Come again?
Yeah,
do you
Kumini's
mean?
theorem. Split it into two integrals, so it'll be easier to do the cosine theta plus sine theta. Yeah, you could have done Kumini.
You could, but it wouldn't make much of a difference though.
Huh?
Computationally, it wouldn't make a difference.
Yeah, but easier.
I mean, if it's easier for you to visually see it that way, then yeah, you can do that. Right? You could actually. You could write this as the integral of cosine theta plus sine theta d theta multiplied by 1 to 3 r squared. You could do that, but I've seen students try to apply this and do it incorrectly. So I usually don't do that in class, right? Because sometimes there'll be like a r inside this thing and they not see it. Yeah, I've seen students mess up with things like that, so I don't usually like to pull that one. Right, so anyway, we have 9 minus a third is what? It's what?
8 2/3.
Come again?
8 2/3. 26 over 3.
26 over 3?
Yes.
And so we would have 26 over 3 times integral of cosine?
Negative sign.
Positive sign. Integral of sine?
Negative cosine.
Minus cosine. Okay, so this 2 times 26 is 52. And if I plug in pi into sine, what do I get?
0.
Pi into cosine? 1.
1.
Negative 1. Plug in 0 into sine, 0. 0 into cosine.
1.
So this is 1 plus 1, right? That's just 2. And so we have minus. Those are all the examples I wanted to do for Green's theorem, but there are some things you can note. Note if the vector function is this guy, then if f is conservative, your qx equals py, which would implies that qx minus py equals 0, which would mean Green's theorem would give you right away that your line integral of p dx plus q dy
Is 0.
is just the double integral of 0,
It's just constant.
which is 0, right? So Green's theorem, it's consistent with what we've said before about conservative vector fields. We're on a closed curve, and if these partials are the same, then the double integral will actually give you 0. So just notice that everything is falling in line, how it should. One more thing to mention, which mostly is for problems on the homework. Area. You can compute area by the following integrals. The line integral around c of x dy. You can also compute it by minus the line integral around c of y dx. You can also compute it by 1/2 the integral of x dy minus y dx. And can anyone see why that is? You can prove these directly from Green's theorem that that gives you area. The area of D.
Of any given D?
So example, right? In the first one. By Green's theorem, if you wanted to apply this, what would you get? The P would be what? For the first integral.
Means
P would be 0.
0.
Q would be x, right? So your Py would be 0, your Qx would be 1. And so the line integral along C, this particular line integral, would be the double integral of this minus that, which is just 1 dA, which we know from Calc 3 is the area of P. Right? So all these, if you actually apply Green's theorem to them, you get precisely this integral. And so doing any of these line integrals is actually equivalent to doing the area.
This is going to get you 2.
Right. Right. So in the case where your double integral to find the area of some region is really ugly, you could also equivalently do any one of these line integrals and it will give you area also. Parameterizing the line curves might be easy, right? But that's just something you should know. And that's it. Are there any questions? Yes.
So you're saying all those is equal to Green's theorem?
No, Green's theorem is just, I'm just showing that it's equivalent to saying that if your C is a closed curve and this guy is conservative, you will get 0.
You're wrong also.
Come out for the other.
Yeah. Because what do you call it?
No,
Right.
these integrals all give you area.
It's still going to be negative b.
And you know they give you area because by Green's theorem, they all give you this.
And it's b, right?
They're not Green's theorem. They're just saying you can compute area by doing this.
It's the anything.
It is minus this, right?
Sure?
B minus A.
Yeah, once your C encloses an area, yeah.
I think it's yeah.
B minus A.
We'll see.
right?
We'll see. We'll see. who's
So for
wrong.
example, if I gave you a circle and
No,
I asked you to compute this line integral,
Yeah.
you just know the answer is going to be higher
Last
squared.
point.
It's going to give you the area.
It doesn't matter.
Correct.